All right. Well, just one notification before we start. I will assign homework probably by the end of today. And with homework, you can have a week. Not you can. You have a week to turn it back in. It is assumed to be turned in class. If you turn it by the end of the day and not at 11 o'clock, then you will be 10% off will be taken, but you can still turn it in a little later during the day. And in that case, you leave it somewhere in my office on the door, under the door somewhere. I have a box for homework in front of the, it's a clear plastic box on my door. If you can't get into my office and there's that glass door drawn, then there is actually a pouch, a plastic pouch outside of my door where you can also slip the homework in. So that's in case you're submitting it late. Otherwise, you are expected to bring it to class. So if you do have something out of the ordinary, you might be going in, I don't know, for an interview or something of that sort happening, do let me know and we can always negotiate turning it in a little later. But that will be done by case basis. I do have to know about it in advance rather than the day of the homework. Oh, by the way, did you know that I went for an interview and I couldn't turn the homework in? In that case, you will not be able to turn it. So that's just to teach you time management skills. So if you know something in advance that is preventing you from submitting homework on time, I need to know about it in advance and then we go from there. Okay, so that's the homework, and homework will be handwritten this time. Starting next homework, probably I'll start putting in little computational assignments that will be sort of like in MATLAB, mostly in MATLAB. So if you don't know MATLAB or anything similar, I don't prescribe that it has to be MATLAB, but MATLAB is easy and available, and it's useful to know something like that. Then start brushing up on MATLAB as you need to. In my lecture 1, I had some links to videos that can help you recap some basic MATLAB fundamentals. There's so many online courses you could possibly take that it's an easy find anywhere online. If you want me to provide you with the sort of what I teach in undergraduate course, I go through MATLAB fundamentals. I have those lecture notes easily available. If that's something you want to do, let me know and I'll post that. So there's actually too many ways to learn MATLAB, not just one. So again, and you will with practice be better at it. Yes?
So you will give us the .m file, or is it?
No, I will likely ask you to write a file. And I will probably not even say what I will, so you're graduate students, so you will organize your .m file the way you want. I'm not going to say create .m file with this name and this function and this and that. So,
okay.
But you will just be required to come up with a solution. Okay. So again, this is in undergraduate class. I say create M file with this name and this function, right? So organization of the code is up to you. All right. So with notes on homework out of the way, let's get back to the course. So we have been discussing molecular basis for viscosity, and essentially we covered the Newton's law, and we started briefly on molecular basis for viscosity of gases last time, and we are now continuing. So this is somewhat unlikely that you went through this in your undergraduate course, other than just like ready-to-go formulas. So I asked you to read chapter 1.4 in advance. So what is our motivation for going down to the molecular level? Our motivation is to find the theory, or rather the mechanisms that are at play, that explain the behavior of gases and liquids, in particular the viscosity behavior. So when we measure viscosity on this sort of macroscopic level, what we observe, and this is simply me plotting table of experimental measurements that is available in your textbook, then we actually see that viscosity of gases increases with temperature. And it does so in this particular range, it does so in a linear way for air anyway. And viscosity of liquids in this particular example of water is sort of decreasing non-linearly with temperature. So we would like to have some theory that would explain this behavior and in particular give us a formula so we can calculate what viscosity is for either gases or liquids, and that formula should actually show this behavior. Okay, so should roughly behave as these two plots of experimental measurements. So let's get to it. Our approach is going to be to assume pure gas at low density, and that will enable us to assume kinetic theory assumptions. So basically we will model gas as a bunch of tennis balls that only elastically collide, so they don't lose energy when they collide. And we're going to impose gradients in velocity, just like we did in Newton's law between two parallel plates. Okay? And then I'm going to actually calculate the flux of x momentum in y direction. Okay? And that calculation, using kinetic theory formulas, should give me an expression for viscosity. And based on the expression we get, we will actually see whether Newton's law was valid to begin with, or whether that assumption was correct. So far, all I'm doing is I'm placing myself in the situation of that basic Newton's law that we talked about. Okay. So let's get to it. So first, if you remember, what Newton's law said is like this was based on the experimental observation. Newton said, I see that this flux of x momentum in y direction, okay, is proportional to the gradient of velocity in x direction. And the coefficient of proportionality is mu. And we have a minus in here because, of course, when I put things in the coordinate system always goes from smaller values to larger values. And in real life, things flow from larger potential to smaller potential, so they typically flow against the coordinate system. So this was something that was just observation of the nature. Now let's see if we can basically, using theoretical assumptions on molecular level, can we actually scale up to something of this sort? So kinetic theory assumptions are that the gas molecules that we have are rigid balls that collide, and when they collide, they don't lose energy. So that's called elastic collision. There are no other forces between those balls, so there are no attractive forces that you typically actually have in a realistic situation. We're going to adjust for that later. But for now, we're just doing a simple assumption. And to the first order approximation, if I have a relatively low density gas at regular conditions like regular temperature, nothing excessive, then that should work out. Okay? So we will also assume the distances between these molecules are large, so we don't have a lot of these collisions. So the moment I get closer, any kind of simplistic explanations about the intermolecular forces will not be correct. Okay? So the closer the molecules are, if you assume that there are any attractive forces or repulsive forces between molecules, that's wrong. We know that's wrong. Okay? So the further they are from each other, that assumption holds better. Okay? So in this particular case, we're going to assume that, and also we have enough molecules statistically we have enough molecules to actually do a statistical analysis of the behavior. Okay? All right, so kinetic theory results that we're going to use, and in your homework you will actually derive some of these formulas just to see how it's done. Basically you will assume statistical distribution of velocities for these molecules, and basically by essential integration, you're going to come up with these formulas. Okay? So you will see how some of these formulas are done. Those are exercises in chapter 1 in the textbook. But for now, just trust me that these formulas hold. So if I actually first define that n is the number density of molecules per unit volume, so simply number per volume, and lambda is the mean free path between collisions. So statistically, I have these molecules colliding, okay? And the average distance between two collisions, okay? So I collide here, and next time I collide is here if I'm this molecule, okay? Then basically average distance for such behavior is called mean free path, okay? So this mean free path depends on, of course, what is my number density, and it depends on the diameter of these balls. So I'm assuming each molecule is just a rigid ball. Okay? So D is diameter and N is number density. And then, okay, if I have, so I'm monitoring this molecule, okay? It collides here and then collides here. On average distance between these two positions is lambda. Okay? That's a distance in space. Okay? If I'm looking at, for one of the directions, let's say this is my y direction, okay? There is a planar distance between these two positions, or it's a y-coordinate difference. That I'm going to refer to as A, okay? So this is distance between planes of collisions in y direction or x direction or z direction, doesn't really matter because we're assuming isotropic situations, so behavior is really similar in all directions. So then this A is 2/3 of lambda. Okay? So those are the results from kinetic theory. Another result is that if I have average speed and my velocity, so I have average speed, speed is just the magnitude of velocity vectors. These velocity vectors are in all possible directions, okay? And they're uniformly sort of distributed all over the place, but the average speed for these molecules is related to temperature via Boltzmann constant. Okay, so Boltzmann constant is constant that relates energy of the molecule to the temperature. And this is mass of the molecule, and P is simply 3.14 and so forth. Okay. So this is again a result from kinetic theory that we will be using. Finally, the number that we need is the frequency of molecular bombardment on one side of a surface exposed to gas per unit area. I'm going to need a prop for that. And my prop will be a sheet of paper. So if this is a surface, a planar surface that we will actually consider, and this is going to be a surface in our derivation that is orthogonal to a y coordinate vector, okay? So this is what I call y-plane. Okay? So this y-plane, if I actually have molecules on one side of it, or the other side of it, either way. So on one side of it, I will have collision with this plane. So molecules, they collide with each other, but they also collide with this plane. So basically, if I integrate collisions over that plane, I'm going to get a frequency of bombardment on one side of this plane, and that frequency is, for some reason this is not shown, but this is 1/4 and u. That u average is the average speed, and n is the number density. Again, you get that by integration, so it's not necessary. You're not supposed to see the formula and say, oh yeah. You need to actually integrate to get that. All right. So those are the formulas that we're just going to take as given. So just before we actually start computing, okay, we need to compute flux of x momentum across y plane. Now I actually defined it in 3 different ways last time, but 2 of them are going to be the ones that I'm going to discuss here. So what is our momentum perspective definition of this x momentum flux? We had a force perspective and momentum perspective. And if you remember, I mentioned last time that depending on the situation, one or the other is going to be more useful. Well, in this case, I'm going to say that momentum perspective is going to be more useful. What is momentum perspective? How do I define tau yx, or flux of x momentum across y plane? Do you remember? What is tau yx?
Transfer x momentum in the y direction.
Okay. So basically, I'm going to have x momentum of particles. Okay. They're colliding with each other. And if I actually have a larger velocity on the bottom, right? And so I have a gradient in y direction of these velocities. Okay. Then due to the molecular collisions, I'm going to see the transfer of actual momentum across that y plane. So basically, this flux happens because I have differences between different layers of fluid in x momentum. Okay. So you can see like that I fitted that into my Newton law when I was explaining things. So you can actually see that this is a derivative of momentum. If you assume constant density of the fluid, you can basically divide mu by rho, okay, and simply sneak in rho under the derivative sign. And once you do that, you see actually the flux is proportional to the gradient of this, or differences in momentum itself. Okay? So that is my momentum view. My flux view, just to juggle your memory, that we're not going to use here, is I kind of divided the fluid in two different portions, and it felt like because of the larger velocities of the bottom portion, it kind of exerted a shear force on the top portion, right? So I say that the force, there's a force in x direction, okay, this force that is sort of pulling this top part because of the larger velocities below. So I can look at it as a force exerted on this entire plane. So do you see the conceptual difference between flux actually moving upwards and actual force? Both of them work, both of them are useful. Okay. So we will actually now test whether our technology here is working, and I'm going to attempt to write on this tablet here and project it on the, project it on the screen. So just a little bit, I need a moment to actually get there. And let's hope it works. This is a new system, so I haven't tested it really. We'll see now. Okay. And now. Okay, so this is how you see it, okay? Okay. So I'm going to attempt writing, oops. Is this visible? Sort of. Screen resolution. Is this better?
Yeah.
All right. It's a little thicker is better. Yeah. I'm gonna actually attempt to adjust pencil here. Okay. This even better? All right, so we will work on this to see what projects the best. So as I go, if you need me to adjust, please say so, and we will play with it until we find the optimum. All right, so good news about this is one can actually erase things. So there are two benefits of this approach. A is I can project on the screen, therefore my camera or my screen capture can capture it on the video. Two, when I save this file, I can save it as notes, and I can post those notes for you. Okay. If I use just this, then I'm writing on a paper that is A, not projected, so I'm not capturing it on video, and I actually have to scan it through the scanner to post these notes. So hopefully this behaves. I'm in a very awkward position to actually connect here, so if I'm making like all of the exercise, or I look like I'm exercising, I'm just trying not to disconnect anything. Okay, so bear with me here. All right, so let's get to it. So my tau yx, okay? My tau yx is the flux of x momentum across a plane of constant y, and I'm going to use my prop again, which is simply a piece of paper. So if this is my plane, okay, I'm going to draw it here, and I'm going to draw it here in red on the side. Okay? So I have plane at y. This is my position y. Okay? And I'm wondering what is coming across. Okay? Well, what did we say about the collisions? If I have a molecule that is going up across this plane, okay? This molecule had a last collision at which distance? Planar distance A, real distance lambda. Okay? So it had a lot, let's say that it collided with the plane right here. Okay? The last collision was here. Planar distance is A, actual distance is lambda. Okay? Same thing statistically if I came from above. Okay? If I came from above, my last collision was all somewhere here statistically. At actual distance lambda, planar distance A. Okay? So I have a molecule that is, for instance, coming in here. And it's either coming from y minus A or y plus A, right? So it either came from here somewhere, or it came from here somewhere. Okay? And this distance is lambda, and this distance is obviously A. Good news is I can erase. Okay? Now, what is tau yx supposed to do? Well, tau yx is statistically then the transfer, or the ultimate absolute transfer in y direction, is x momentum of all of the particles that went upwards minus x momentum of all of the particles that went down. We are looking at things in statistical sense. I know that if I have more velocity, my velocities are bigger here than here. On average, I will have a transfer upwards. But that doesn't mean that no molecule passed downwards. Okay? Some of them still did. Okay? They collide, they bounce around. Some of them go up, some of them go down. But momentum that are of those down is overall larger because they have larger velocities. And so I will ultimately have transfer up. Do we agree on that? All right. So let's just formalize it. So this is essentially x momenta of molecules going in plus y direction minus x momenta of molecules going in minus y direction. So if I just have one molecule that is crossing this plane upwards, okay, its last collision was at y minus a. It's not going up, right? So I collided here, and now I got bounced off, and I'm moving up. Okay? So I'm carrying the momentum from position y minus a. Is that correct? What is that momentum? It's mass of the molecule times its x velocity evaluated at y minus a. Is that correct? That's one molecule. Statistically, how many of them I have crossing this plane upwards? Z. There was that number I defined, which is precisely, bombardment, and that's actually the number of them crossing up. So it's bombardment, average bombardment, or frequency of bombardment of this plane on one side, which is downside. Okay. So that is my total momentum moving upwards. Okay. Now, if I'm actually a molecule that is going down, my last collision was somewhere up here. Okay. So I'm carrying that momentum. Okay. So if I'm going down, I'm carrying actually a momentum from here. Okay. And that momentum is Vx evaluated at y plus a. And again, I have z of those bombing my plane, okay? And I have to subtract. Cool, now we just need to see what these velocities are. Now, I'm doing statistics on molecules, so I have enough of them working, that this A or lambda, they're statistical, therefore to just even compute them, I had to have enough molecules to do that, right? So I have quite a bit of molecules moving around here. So these distances are large enough to capture enough molecules. So, okay, I have to have some velocity distribution here. And as is, I placed myself with Newton's law, so I said that somewhere down I have a plate that is moving at some maximum velocity Vx, and somewhere up from here I have a plate that is standing still, okay? And I have a linear, I can assume that on this small of a distance, I for sure have a linear distribution to the first order, okay? And that, in these kind of, with this kind of granularity, I can definitely assume first order. So we will assume linear Vx around point y. Okay, if you excuse me, I will try to adjust this just a little bit. It's kind of not, maybe 5, something like that. It's kind of hard for me to see and write. Okay, so basically, if I'm assuming linear, then my velocity Vx, yeah, that's better for me. Do you all see still? At y plus a is essentially my velocity evaluated at y. And then according to Taylor's formula, plus the distance a dvx dy. Right? And I'm chopping off all of the second order terms. Yes?
We are assuming at a local level velocity profile is linear. Does that automatically translate into assuming that the fluid is Newtonian in the microscopic sense?
Not really. So I'm still on a small box. I'm still in a local sense close by. It will end up upscaling. That will, yes. So upscaling wise, we will actually get the term and it will turn out to be Newtonian, but right now I don't know that. So that's a great point. Like if I already assume this Newtonian, what am I proving here? Well, I'm also maybe finding a formula. Okay. So essentially this is my Vx at y plus, and same thing if I had a minus in there. Oh, hi, wrong. So if I had a minus here, I would just have a minus here, okay? So now I replace these two. Okay. So this first one will be Vx at y minus a dvx dy, okay? And the second one will be Vx at y plus a dvx dy, but I have a minus in front of it, okay? So what I'm really getting here is that this is equal to minus, and then these two parts will cancel, right? Everybody sees that? So if they cancel, all I'm left with is two terms like this. You okay? Z is Z. This term cancels, and then I have minus a dvx dy times zn minus a dvx dy times zn. So which is minus two of them. Okay. Time to plug in what is this. Okay. This was 1/4 n average u. This was 2/3 lambda. So that's 2/3 times 1/√2 p d square n. If you also recall u, I'm going to choose a green. U over here is square root of 8 kappa was a Boltzmann constant T divided by Pm. I'm going to work out in a moment what this mumbo jumbo of terms actually is. But before I do that, what do I have in there? I have that number density, which I knew I could compute. I have, so that's something that I have. I have average U, which is simply a function of temperature, which I measure macroscopically, and mass of the molecule. So this is really a property of the fluid, of the gas that I'm looking into. I have lambda or A that is ultimately expressed in terms of diameter and the number density. Okay. So there is nothing in these terms, even though I have velocities here, okay, there's actually nothing in this term here that is related to the macroscopic velocity Vx. This is just the average molecular velocity, okay, that I can compute just based on temperature. This has nothing to do with the imposed velocity from the outside. That comes in here. All right? So essentially, I have nothing in here that is a function of Vx. It's only a function about molecular characteristics, diameter, mass, temperature, and constants such as P and kappa. And number density of fluid, which is ultimately related to the density of the fluid, right? So I have actually arrived, whatever this mumbo jumbo ends up being when I work it out, okay? I have that tau yx is negative times something in terms of macroscopic properties of the fluid, either measured or in name, n times dvx dy. So I have arrived in, when I compare that to what Newton came up with, then this mumbo jumbo here, 2zma, whatever it works out to be, is my viscosity. Okay? And I have a formula for it. And it's this kinetic theory that is completely independent from what Newton has thought of, okay? He just observed, that basically confirms my general, or his general thinking to this first order of approximation. It is a simplistic theory was true. Okay? So that is a very strong result, even if I have approximations. Questions? All right, so let's now write down what this formula really is. I'm actually just going to refer to the slides from here on. So I'm just going to say, I'm going to see if I need a new one, but actually, I have say, I'll just go to the and this is the part, but I'm just going to disconnect this. Okay. And now trying to get out of this software is always a bit of an issue. Control V. Okay. All right. So when we actually work out all of the details, and that's a simple algebra, you will actually get that you have here 1/3 times n times m times u average times lambda. Okay? So that means that my viscosity is 1/3 of n times m times u average times lambda. And when I plug in all of the formulas, mu turns out to be 2/3p. P is just 3.14 and so forth. Square root of p, mass of the molecule, Boltzmann constant, temperature, this is microscopic temperature, divided by d, which is diameter of the molecule, d squared p. And the reason why it's written this way is that d squared p is often called collision diameter of the molecule. Or cross-sectional, collision cross-section, really. Okay? So this actually formula confirms Newton's empirical observation. Okay? It also tells me that in terms of temperature, which is what I was actually wondering at the very beginning, is proportional to square root of T, right? So that means that as temperature increases, my viscosity increases, and that is observation that we have from experiments for gases, okay? And I don't seem to have dependence of pressure, okay? It is in there. I can, if I assume ideal gas law, I can plug in and make this formula to be in terms of pressure, but there is no both pressure and temperature in there to begin with. So it's either on either, dependent on either of those if you think about it. All right. So again, if I ever quiz you now, what is this formula mean? Will I expect you, what do you think, or will anybody realistically expect you to spit out the formula precisely? What do you need to remember about it? Precisely. So you have to have this idea, okay, it's proportional, so based on the kinetic theory of gases at low density, what is gas viscosity proportional to? Okay? Is it 1/t? Is it square root of t? Is it t? Is it t squared? What is it? Right? So those are the things that are important to remember. So if I wake you up at 1 a.m., I expect you to know the answer to this question. That other formula, you cannot wake me up at any time and expect me to remember that formula other than just 2 minutes after I used it last night. Okay? So you put that formula, if you want to start assembling your cheat sheet that you will have during the exam, during your homework, you will be able, cheat sheet is a piece of paper such as this that you will be allowed to have in terms of formula on your midterm. Okay? So as you're working on homework, start, neatly writing little boxes with the formulas that you will need. So this is one of those formulas that you want to put down on the cheat sheet. So as you're solving homework, it's not a bad idea to start putting that together. That said, whenever I created cheat sheets in my school experience, I would make them just before the test, and then I would never even look at that cheat sheet because I would actually remember. That was kind of part of the review. Whatever works for you. All right, so this is the formula. Again, what you need to remember is square root of C. All right, now we assumed, and we made a pretty bad assumption, that there are no intermolecular forces at play. And these are some sort of magic balls that just collide with each other and there's nothing else. Well, that's bad, we know that. Okay? We actually know that as molecules are far from each other, I have attractive forces. As they get too close, then they will start to repulse each other. That's sort of some sort of self-preservation, you could think about it that way. And there is some sort of critical distance in between these distances that somewhat depends on the molecular size, okay? That this attractive forces turn to repulsive and the other way around. And the most common formula or functional relationship that actually describes this behavior is using potential. That potential will be a function of distance r between the two molecules, and my force between the molecules will be a derivative of potential. That's simply how things are modeled. And the most commonly used one that basically models really well what's actually measured. You can measure forces, intermolecular forces, with the atomic force microscopy. Okay? That's what chemists do quite a bit, and there are tables of these, but basically the most common used is Lennard-Jones potential, and for all intents and purposes it's a very good model and agrees with experiments really well. So basically it says that. So if I actually have this potential, okay, I will see that I have 1 over R12. So 1 over R12, as R becomes really small, becomes really large, and much larger than 1 over R6, which is the second term. Okay. So basically, the first term is dominant for small distances R, and the second term is dominant for large distances R. So for large distances R, much larger than this magical sigma, which we call collision diameter. Okay. For those, I have the number that is larger than 1, and to the 6th power of that number will be dominant over to the 12th power. So basically, you will have that behavior here. So phi is actually plotted here. This is a normalized, and it's normalized by this epsilon, which is the maximum energy of attraction and depends on the molecules that we are looking at. Okay. So we have these things tabulated for different gases. Okay. So if phi is this, then basically your force is blue line. Okay. And I will likely ask you to plot this for yourself for homework as well. And if those, we are not going to go through the derivation, but if I take into account these type of forces in between molecules, then there will be a correction to the formula that I've shown you. And integration of those forces brings in new term. There's omega here that comes from integration of those forces. The rest of the terms are very similar to what we had in our previous kinetic theory. Okay? And basically, you can do it in different ways. Again, this is not something that I will ask you to remember, but just know roughly that this formula exists and where can you calculate it. But you will look up this omega in table E2, which is appendix E. Anything with letters is appendix in BSL. And this is tabulated as a function of macroscopic temperature. And epsilon is maximum energy of attraction that you also look up based on the molecule you're looking for. And then when you plug it in, if you use the units in table E2, then you should use angstroms for sigma. Okay, these are also measured. Molecular weight is molecular weight, and you should use viscosity in CGS system. And when you plug into this formula, you can calculate. So this is, again, we're not going to go through the derivation, but assuming that we can accept this, let's see what the limitations are and how well does it work. Okay. So this is derived for, again, monatomic gases and can be used for some polyatomic gases as long as they're not polar. Okay? Or don't have these molecules that widely differ from my assumption that I have a sphere. Okay? So if you have like some huge chain in their hydrocarbon, it's not going to work. Okay? And for mixtures, you could also adjust it. That again, I'm just going to ask you to know about it, and you're going to do some homework to remember that there is such a formula. But if you have a mixture of different molecules, none of the theory that we had here before applies directly, because I'm not going to have Lennard-Jones potential for two different types of molecules. Okay? But there are adjustments that are based on the actual fraction of each gas that you have. Okay? And if you want to go, so there's simply these things you just simply compute based on the tabulated versions. And empirical results can be found in this test, so you can also simply go for experimental measurements. Now let's see how it works. So experimental data are here points for air. Kinetic theory assumption, it follows the correct trend, but it comes up short. Okay. So we captured something, right, using that simplistic theory that we were actually able to derive. But it's not all the way correct. This correction, which is called Chapman Enskog theory, that calculated in Lennard-Jones potential and my weakly attractive and repulsive forces between the molecules, that worked really well. Actually, so repulsion gets strong, attraction is always relatively weak. So that actually is pretty much right on the money. And this is for simple, air is a relatively simple mixture of gases. So this should work well in this range of up to 1,000 Kelvin, which is more than enough than what we need. Okay. You have oxygen, for instance. You can also look at it at different pressures. Okay. So kinetic theory prediction is again coming short, but so does Chapman Enskog theory if I have very high pressures. So I'm constrained at relatively moderate pressures. Okay. So you always have to ultimately, thinking about petroleum engineering applications, you are working at extreme pressures and extreme temperatures, so looking up empirical data, if it exists, is sort of the best step. Okay. But often when you're testing an assumption, or you're coding something up, a simulation, and you need an assumption to go with, even if it's a first order assumption, then formulas like these are extremely useful because they can be simply coded up. There's a formula that can be coded up, right? And I can go with it until I discover that it's not enough. Okay? So this is how any kind of theoretical formulas should be created. You go with it, knowing your assumptions, and use it until you somehow prove it to yourself that must be something that is wrong and you should actually look for alternatives. Okay? All right, so let's continue on Friday. Read chapter 1.5, please.